Hello, good morning, and today we are looking at negative exponents. And you might be saying to yourself, Self, I'm done. I'm out. Exponents are hard enough, and now he's making them negative. Yes, that's right, but it's really not as hard as it sounds. Again, I think it's just kind of maybe some math anxiety that can bubble up and make us think that things are worse than they are. Negative exponents. What does it mean? Well, first of all, what does an exponent mean? Exponent means, I hope you're saying it in your head to yourself by now. Exponent means repeated multiplication. I'm going to break this down for you here. Negative is another word we think of as opposite. Okay? So a negative exponent equals repeated, not multiplication, because what's the opposite of multiplication? Division. Okay? It's division. So negative exponent equals repeated division. Did I say that right? Negative exponent equals repeated division, and a positive exponent equals repeated multiplication. Okay? So this should make sense in that way, where 2 to the third power equals 2 times 2 times 2. Another way you could think of this is 2 over 1 times 2 over 1 times 2 over 1. Why would we think about it like that, Melly? Well, because if this means repeated multiplication, 2 to the negative third means repeated division, which is 1 over 2 times 1 over 2 times 1 over 2, which is really, right, if this is equal to 8, that means this is equal to 1/8. Okay? So another way to write this, 2 to the negative third, is equal to 1 over 2 to the third. This is actually the definition of what a negative exponent means, but it gets you to the same place. So in general, a to the negative n equals 1 over a to the n. This is an important one to have down. And again, as an example, 3 to the negative fourth power equals 1 over 3 to the fourth, which is 1 over 81. Sometimes it's helpful to have like a concrete example right next to a definition. So that's what that means. How does this come into practice? Well, we often have negative exponents. This comes into play in the real world in terms of things like exponential decay. So when things are decaying exponentially, this could be like a substance that's radioactively decaying. We also have funding balances that can decay at a constant % rate of change. So these actually come up a lot, and it's not just something fun that we do in math class. And it represents this reciprocal type thing where we're dividing instead of multiplying over and over. Okay? Regardless, we need to learn the rules of how they play with the other exponents, and so we're going to do that through example as well. So if I say simplify, usually we want to get rid of negative exponents. So usually we write final answers without negative exponents. And the reason why is because it's easy enough to go from here to here, right? It's easy enough to go from here to here. So if I said simplify, say I had a to the minus 2 over ab squared. How would we rewrite this? Well, what do negative exponents really mean? Negative exponents really mean repeated division. So one way to think about this is really 1 over a squared times 1 over ab squared. And then we can simplify this to be 1 over a squared times b squared, and then just simplify. How many a's do we have? How many b's do we have? Okay. Something that, other algebra videos and tutorials will teach you is just, hey, just switch it, pop it down to the bottom. That's okay. Again, but why does that work? Well, it works because negative exponents really mean repeated multiplication. So or repeated division. So when we rewrite it as division and then multiply things together, we'll always end up with the right answer. Okay, but it can be helpful because what it means is that I'm not in the right place. Right? It means you're supposed to be dividing by me, not multiplying by me. So let's do another one here. So if I had x to the minus 2, y to the minus 1, over x to the third y. Again, try this yourself. See what you think this should be. I'm actually going to tack on a z here. Say we had a formula that looked like this. What would this look like? Well, this is really 1 over x squared, 1 over y times z, all over x cubed y. And then we can regroup, right? X squared, x cubed, y times y, x to the fifth, y squared. Okay, so not too bad. Now, what can be a bit of a challenge or an initial shock is if you see a negative exponent in the denominator, right? What the heck does that mean? Well, if I had x to the third y squared over x to the minus 2 y to the third, right? How would I deal with this? There's a couple ways you could do it, okay? This is one of those places where it might just be easier to remember that the negative means the reciprocal, but I'll show you exactly what's going on, okay? I'm not going to sugarcoat it for you. So the top, x to the third, y squared, all over, what did we say x to the minus 2 was? 1 over x squared times y cubed. Now you might see we've got a fraction within a fraction. That's okay, right? That is okay. Because what does this really mean? Well, it means that I have this whole thing over y cubed times 1 over x squared. And what do we do when we divide by a fraction? It might take you a second to remember. Dividing by a fraction, right? If I have 1 over 2 divided by 3/4 is the same as 1/2 times the reciprocal 4/3, right? Which becomes what? 4/6 and becomes 2/3. So dividing by a fraction becomes multiplying by the reciprocal. So this really becomes x cubed y squared over y cubed times x squared over 1. Right? If I'm really dividing by 1 over x squared, it's like I'm multiplying by x squared over 1. So it's a lot simpler than we thought. So then the top can resolve. We'll get, coming down here to the next line, x cubed x squared times y squared all over y to the third. And then we can simplify using the rules we know already. And so we should be left with x to the fifth over y, right? 2 cancel up here with 1 down here. Just to be abundantly clear, right? 2 of these canceled with 3 of these. So, what did we learn? If you have a negative exponent in the denominator or in the numerator, it really just means that it is the reciprocal of where it is currently living. So just kind of note this, that, you know, if I have 2 to the minus third over 5, this is really 1 over 2 to the third times 5. And if I have 5 over 2 to the negative third, this is really equal to 5 times 2 to the third over 1. Why is this the case? Because of this right here. When we divide by a fraction, right, since 2 to the negative third is really 1 over 2 to the third, we really go through this process of flipping what we're dividing by, right? So this is the simplified version of that. So this would end up being, what, 40 over 1, and this would be 1/40th. So wherever you see this negative exponent, it really means kind of a to the negative n means I'm in the wrong spot, right? Either numerator to denominator or vice versa. So you can move it and then deal with the exponents as we know them to be true. You're not always going to do this. There is a certain amount of realism where you're going to need to use this shortcut to your advantage, but not before you really understand where it comes from. So do a few in this way before trying this, because this will not make sense until you do that. Okay, so let's do one or two more here of some like medium and hard problems. Okay, so 3 quick examples here. And again, there are many ways to go about this. But I'm going to show you the way I think about it. Okay, so simplifying the top of this fraction here. So we'll start up here. So g to the minus 3 really means I'm in the wrong spot, right? It means 1 over g cubed. It means I'm supposed to be dividing instead of multiplying by g 3 times. One way you could use that is here with this guy on the top. You could send this down to the bottom. You'd end up at the same place. Or you could remember, what does g to the 6 really mean? Well, g to the 6 means multiply by g 6 times. And this means divide by g 3 times. So what does this thing times this thing really get you? Times g, 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 all over 1. 2, 3, 1, 2, 3, common factors cancel, right? And you should just be left with g cubed up top, all over g to the 12th. And then we can go ahead and reduce further. I know I've got 3 up top and 12 down below, so how many am I going to be left with at the end of the day? Should we have 1 in the top and 9 left over in the bottom? Okay. Another way to go about this would have been to send this down and say, all right, this is really g to the 6th over g to the 3rd times g to the 12th. You get g to the 6th over g to the 15th, and guess what? You're going to go to the same place. Okay. So either one is fine, but I do want you to be familiar with this idea right here. And again, what are you seeing as a relationship between these exponents and where you ended up, right? G to the minus 3 times g to the 6th left me with a total of 3 g's up top. Now let's look at this one down here. 2x to the minus 4 to the 2nd power. A couple ways you could see this. 2 over 1, that stays itself. 1 over x to the 4th is what we mean by x to the minus 4. All of this being squared, we could simplify this a little bit. And then say, okay, well, it's this times itself this many times. That's 2 over x to the 4th, 2 over x to the 4th, which gets me 4 over x to the 8th. That's one way to go about it, right? The other way to think about it is to just take it as it is here and say, or this is really 2x to the minus 4 times 2x to the minus 4, which is 2 times 2 times x to the minus 4 times x to the minus 4. So it's, I'm dividing by x 4 times, I'm dividing by x another 4 times. So how many times total am I doing that? 8 times I'm dividing by x, which is really the same as 4 over x to the 8th. Just another way to view it. For this one, this is a different problem. Obviously the values look similar, but what's the difference? Here I have a negative 2 up here. So all of this to the minus 2, what does that really mean? Well, we might be better served by working on the inside here first, just like we've done before, getting that to a simplified place before worrying about this. So again, you could rewrite this as 2 over x to the 4th, all to the minus 2. And then what does raising something to the minus 2 mean? It really means taking what you have and dividing by it twice. So this becomes 2 over x to the 4th squared, right? Which becomes 1 over 4 over x to the 8th. Right, if I simplified this guy here. But then 1 over something is really the flip of it. So we really can rewrite this as x to the 8th over 4. Right? Since 1 over a over b is equal to b over a. That's one way to think about it. Okay, or, and I know I'm going through these quickly, but I'm hoping that you will pause and take time to reflect on each of these things before moving on. So, or another way you could think about this is you could start on the outside and say, all right, this is really 1 over this whole thing squared. And write it out this way, and we know that this is really 1 over 4x to the minus 8. So I'm dividing this many times and this many times. And then when you're at the end here, you say, all right, well, this x to the minus 8, this is really meaning division. It's in the wrong spot, so it should be up top, x to the 8th over 4. Any way you slice it, as long as you're following the rules, you should end up at the same thing. Okay? And it makes sense that when we're looking at these, that I started with the same inner term here, multiplied it, or raised it to the opposite power. Okay, so I started with the same thing inside, I raised it to the opposite power, and what should we get? It should be the reciprocal of each other. Right, so these should be the flip. All right, let's do one more example of these, and then we'll move into rational exponents. Okay, so one more example, and I'm just going to kind of barrel through this one, and hopefully you can follow along. I'm going to use that idea that negative exponents really mean division. They really mean I'm in the wrong spot, but first I'm going to simplify the top and the bottom as best I can. The bottom's good to go. There's no common terms. There's no other x factors or y factors or z factors, but up top we have some things that could be moved around. So I could have x to the minus 2 times x. I've got some y factors and one z factor. And so, right, if I'm dividing by x once and multiplying by it once, if I'm dividing by x twice and multiplying by x once, I should be ending up dividing by x once. Right, if you think about it, this is 1 over x squared times x. over 1. So it should be left with 1 over x times y times 1 over y. And so it should be left with y to the minus 2. And then this z term, there were no other factors up top. And so the bottom hasn't changed at all. And now we're looking to simplify as best we can. So anything with a negative exponent is going to switch locations, right? It means it should be in the bottom or it should be in the top, depending on where it is. So this should become x to the first down here with your x term, y squared. Now this y to the minus 2 should be coming up, and this z to the minus 3 should also be coming up. This is all times the z that was up there. Let's actually keep our z terms together here. So what are we left with? Well, in the bottom we have how many x's? X to the 4th. The y terms cancel. We're just left with 1 there. And how many z's do we have? In the top we have 4. Okay. So a couple notes here. You might have noticed at this point that you could cancel these y's. And you'd be right, because even though they've got maybe some ugly notation, any number over itself is what? Equal to 1. So even if it's y to the minus 2 over y to the minus 2, as long as it's the same number over itself, you could have canceled it there and saved yourself a step. But this notion of if I have a negative exponent, that means I should be in the denominator, or vice versa. If I'm in the denominator, I should be in the numerator. That's a good way to view these things, and they should work out for you. But also, this work that was done here is really important that you start to see these patterns of, y to the first times y to the negative 3 leaves you with y to the minus 2. X to the minus 2 times x to the 1 leaves you with x to the minus 1. What are you noticing about these exponents and their relationship to the resulting exponent? Okay, so I'm going to pause there, and we're going to jump into rational exponents next. I would highly recommend pausing yourself. I'm going to make this one video, but going and trying some of these practice problems before moving into rational exponents, because they're a little bit different. So rational exponents, again, what does it mean? Exponents means repeated multiplication. Rational means fraction, right? Or of ratio. So fraction exponents. You might say to yourself, that sounds awful. And you're wrong. It's not really that bad, and it follows naturally from, again, our basic assumptions and understandings of what exponents mean. Okay? So let me break it down for you like this. So watch and notice here. So x squared times x squared, right? What does this end up becoming? X times x times x times x equals x to the 4th, right? One way you could think about it is that we really kind of add these exponents together to get x to the 4th. Another way to think about it, what about x times x? This is really x to the 1st times x to the 1st. That's like x to the 1 plus 1, which is x squared, right? I have two factors of x. So here's one example, here's another example. But here's a question. What if I ended up with x to the 1st and I added, I don't want to make that a 0, let's make it like a box. What if I added two exponents together to get 1? What could that be? So what if it were like 0.5 and 0.5? or 1/2 and 1/2. Doesn't this work out? Right? What's a half plus a half? Yeah, it's equal to 1. So this should work. But if it does, then what the heck is x to the 1/2? So take a moment and pause and kind of think about this. What is happening here? We have this pattern that, okay, when I multiply like bases, I add the exponents and they should add up to that resulting thing. This resulting thing definitely exists, but if I go backwards from 1 into things that are less than 1, what does this mean? X to the 1/2. Well, it means the number that I multiplied by itself, right, because this is the same as this, to get x. Well, what is that? Well, let me give you an example. What is the number I multiply by itself to get the number 4? Well, that number is 2, because 2 times 2 equals 4. What about the number I multiply to get by itself to get 16? Or let's change that so we don't think it's something else. To get 25. Well, that number would be 5 because 5 times 5 equals 25. So, do you see the pattern between this number and this number? This number and this number? This is the square root of this number. So, x to the 1/2 is really the square root of x. That's what this means. Okay, x to the 1/2 means the square root of x. And if you think about it, it makes sense that the power would be a half, because what it's saying is, what is something that times itself, I get the number to begin with. So in other words, 4 to the 1/2 is the square root of 4, which is 2. And that makes sense because 2 times 2 equals 4. And we know that 4 to the 1/2 times 4 to the 1/2, my pen's goofing up here. I know that 4 to the 1/2 times 4 to the 1/2 should be 4 to the 1/2 plus 1/2, which is 4 to the 1st. So it has to be that 2 is 4 to the 1/2. And same for 25 to the 1/2 power is 5, because this is the square root of 25. This is goofing up on me here. So this is equal to the square root of 25. All right, so we see that 25 to the 1/2 times 25 to the 1/2 equals 25 to the 1st power. So it must be the case that this is 5, because 5 times 5 gets you 25. So in general, this is the case. And this generalizes to x to the 1 over n is equal to the nth root of x. Now what is the nth root? It's the number that it takes this many of it to multiply to get to your number. So in other words, we've talked about the cube root before. The cube root of 8 is the number multiplied by itself 3 times. That's where that number comes in to get 8. And what is that number? 2 times 2 times 2 equals 8, so we say that the cube root of 8 equals 2. Right? Or 2 cubed equals 8, so the cube root of 8 equals 2. It's the inverse operation. But this happens for not just 3 times, but n times. So like the 5th root of 32 is 2. And this is equal to 32 to the 1/5 is another way to write that. Because 2 to the 5th, 2 times 2 times 2 times 2 times 2 equals 32. So, this is an important just notational thing to represent. It represents the nth root. Okay. So, again, x to the 1 over n equals nth root of x. So, how does this come into play? Well, when we're talking about simplifying expressions, really the fact that it's a fraction is going to be the most important. But when it comes to evaluation, finding answers, you're going to be interested in what this number means. Okay. But let's put it into practice with some of the rules for simplification we've generated ourselves. So if I have, x squared times x to the 1/2, what does this really mean? Well, it really means we have x times x to the 1/2. How many x's do I really have? 1, 2 and a half. Right? This is really x to the 5 halves, or x to the 2.5. It's okay to write decimals as well. Usually we want to write fractions so that we can see what the root is, but having a decimal is totally fine for most purposes. Similarly, if I had x to the 3/4 times x to the 1/2, x to the 3/4 times x to the 1/2, well, you could get common denominators here and represent the fractions as 2 over 4 instead of 1/2. That's fine, because then you can talk about how many x's do I really have. Well, I've got 5/4 factors of x. Okay, so it gets a little strange just because we're not used to fractions being in this space, but all of the rules that we've come up with apply all the time. So it even applies in this weird setting where we have fractional exponents or roots of things. Okay, and then also you can have these mixed or improper fractions. And what does this really mean? X to the 5/4 really means I've got the 4th root of x to the 5th, right? Because the numerator means how many of this thing I have, and then the denominator of the exponent means what root I'm taking of it, right? So that's what this means here. So in general, too, you could write this down. X to the n over m is the mth root of x to the n. So here's like an example to go with that. So here's a key skill here. Okay, to write this given radical expression with fractional exponents instead, right? Because it's easier to work algebraically with fractional exponents than it is with these big radical things. So it's important to remember the implied brackets, that this is taking the 5th root of this whole thing in here, right? Which means it's going to be this whole thing to the 5th root is the 1 over 5th power. And then whatever was in there to begin with is just 16g to the 1/5. So for us to do this, key thing is to notice where these implied brackets are. And what this really means is just the fifth root of what's inside. Okay, and last example is to, given a write in radical form, given a fractional exponent. So let's say I had like 3p to the 1/4, and you want to write it in radical form. Well, you have to use this idea right here. Something to the fractional exponent is equal to that nth root. So it means we're taking the fourth root of this whole thing, 3p on the inside. So you have some practice problems with this. There are some worked examples in the text as well. You'll be expected to tackle problems like this and simplify expressions with negative exponents on your upcoming exam. This really tackles all the key skills with exponents that we need, though. So you're in a great spot. And what we're going to work on next is using these in first of all, a place where we're going to be factoring larger expressions, and then using that to solve equations that are no longer linear, right? So we've been looking at linear equations before and working with lines and linear functions, and we're going to start to peer into what happens when the functions are a little bit more complicated than linear and they have exponents. How can we solve equations there? And these skills are going to come into play. So I highly recommend jumping into these practice problems, having this video close by so you can use it as reference, and we'll see you in the class discussion with all your questions.